Testing on YouTube. Testing on YouTube. How's it going? NLP prompter. All right, YouTube is working. Let's test on X. Testing on X. X is working. All right, perfect. Just one last one. Testing on Twitch. Let's go and open room XYZ. Video download was canceled. What the hell does that mean? All right, I can't actually verify that the Twitch stream is working, but I don't think anybody even watches the Twitch stream, so it's fine by me. All right. Let's go in little KM. How's it going, Josh Phillips? Let's go ahead and get this thing started. All right, welcome everybody to another Who Posts stream. Today's stream is called Gspo, FPO, ARPO. Possibly one of the worst SEO names for a stream of all time, but we're not too worried about SEO. This stream is looking over a couple different reinforcement learning papers that have come out recently. People have posted them on the Discord. People have been talking about them on the internet. So we got this one here, Gspo, Group Sequence Policy Optimization, from the Quen team at Alibaba Inc., recently released on the 28th of July, 2025. We're also going to be looking at this one, Agentic Reinforced Policy Optimization, ARPO, also out of some Chinese institutions here, Renmin University and Kuaishou, 26th of July, 2025. And then we're going to be looking at this one. This is Flow Matching Policy Gradients, or FPO, for Flow Policy Optimization, which is 28th of July, 2025 as well. This one is from UC Berkeley and Max Planck Institute for Intelligent Systems. So basically what's happening now is that reinforcement learning has been shown to work for language models. And as a result, we've kind of seen an explosion of interest, and all the different academic groups, all the different industry groups now have some amount of reinforcement learning research going on. So you're seeing rapid pace and progress of reinforcement learning algorithms. For a while, people were kind of stuck using PPO, and then with the DeepSeek R1, people suddenly all moved to GRPO, and now you're starting to see kind of the next step after that, which is kind of a bunch of variants of GRPO. I would say these two are kind of extensions of GRPO, and this one actually is a little bit more interesting. This one's a little bit more low level. This is more just built on top of PPO, but it uses flow matching, which is now starting to bring in some of the kind of diffusion, kind of image generation, video generation, some of the stuff that they do there, right, with flow matching now into language models. Although this one here is not really in language models. This one is still super early, so it's basically just your classic kind of like Mujoko control suites, like Fish Swim, Point Mass, Mujoko Playground. So this kind of is kind of a more classic reinforcement learning playground or reinforcement learning paper where the environments are kind of your toy environments, versus this one and this one are kind of more language models, right? So going Julien, short vid, Cheb Khalid, power of open source. Yeah, and maybe that's a good place to start, right? So open source basically should mean that you let other people do the thing, right? You kind of instruct them on how to do the thing. You publish your code. You hopefully kind of publish the data. But we kind of saw this weird situation where people would publish the inference code, they wouldn't publish the training code, they wouldn't really publish the training data, but they would still call it open source. I think now with reinforcement learning, it kind of solves one of those problems, because at least you don't need to publish the data, right? In kind of the pre-training paradigm, the data is kind of like 90% of the equation. So not publishing the data in the pre-training paradigm and calling that open source doesn't make any sense. But whenever you're doing reinforcement learning, right, the data is generated by the model. So you're kind of like generating the data that you use to train. Kind of you train as you generate as you train. So the data is a little bit less important in reinforcement learning. Not less important in the sense that it doesn't matter, but less important in the sense that if they don't tell you they don't give you the exact data that they train on, it doesn't really matter, because you're going to be generating your own data, or if you're going to use this RL. But okay, so this group sequence policy optimization, if you actually go to the Hugging Face, right, here's the actual Hugging Face paper page. You can see a bunch of upvotes here. Although recently I don't really trust these upvotes anymore. I think much like any other kind of social like or upvote system, people have figured out how to game it. And I kind of see this pattern where, especially papers that come out of some specific Chinese institution, they'll have like hundreds of likes, right? So I think there's probably these kind of like how people figured out how to game the GitHub stars, and there's like these weird third-party companies that will give you like 1,000 GitHub stars if you want it. I think there's starting to be, I don't think there's third-party companies to give you upvotes on the Hugging Face paper page, but there's probably group chats or kind of things like that where people say, hey, here's a paper, they put it on this group chat, and they can get like 100 people to upvote it. So I don't 100% trust these, but the important thing I wanted to talk about here is you have the paper author here who actually created this post, and then you kind of keep scrolling down here, and then eventually someone asks the question here. So any open source implementation, right? And you basically have two different people comment. You have the original paper author here, and he points to this PR in the VERL repo, and then you have a Hugging Face guy. This is the GRPO, Open GRPO guy. He points you to the TRL. So really the two main implementations of this, I guess you have another one here, MS Swift, but the two here that I want to point out here are this VERL and then the Hugging Face TRL, right? So these are kind of the two big reinforcement libraries that are reinforcement learning libraries that people are starting to use, and I think mainly got popular because of their GRPO implementations, right? And these are pretty active, so you can see they have over 10K stars, right? So this one also has over 10K stars. You can see here they're pushing code. People were pushing code yesterday, right? So there's a lot of activity going on. But I thought what was interesting here is if you hover over the people, so look at this guy, hover over this guy, and then you can see the location here. So this guy is from Vancouver. Okay, Vancouver, Canada. Hover over this guy. No location. Berlin, Germany. Hover over this guy. Bern, Switzerland. Hover over this guy. Bern, Switzerland. Hover over this guy. Calgary, Alberta. Hover over this guy. Philadelphia, PA. So you can see these are all Western people. If you go into this one here, the VERL repo, completely different story. Hover over this guy. No affiliation. This guy. Beijing. This guy. Hong Kong. This guy. Shanghai. This guy. Beijing, China. This guy. Suzhou. This guy. Hangzhou. This guy. Beijing, China. So there's a very clear kind of story here for me where, hey, you have this hype paper that gets pushed. People ask for the open source implementation, and then you have basically two different competing implementations. You have the kind of Western European kind of open source conglomerate represented by the Hugging Face and TRL library, and then you have the kind of Chinese Asian implementation here with VERL. So I thought that was kind of interesting. Julien, I mean, you're comparing one Hugging Face repo versus one ByteDance repo. Yeah, and there's more, right? So like, for example, this one is here as well. So I think they have another one here, MS Swift. Let's see this guy. Model Scope MS Swift. GSPO. What are these guys? Hangzhou. Nothing. Hangzhou. Nothing. Nothing. This one's a little bit more anonymous, so maybe more kind of decentralized Hangzhou. A lot of Hangzhou people here. But yeah, so even though open source is supposed to be kind of decentralized, right, you're seeing kind of these clusters. Model scope will be Chinese too. How's it going, Ed? It's a Chinese Hugging Face copycat. Yeah. But, okay, I mean, if we actually, so let's actually look at these PRs, right? So ultimately, GSPO is just a PR, right? And most of these PRs aren't actually super complicated. So here's, for example, is the Hugging Face GSPO PR. And you can see they really only changed 6 files. So you can see, let's look here what they did to the config. So what did they add to the config? Really just added this one option here, which basically allows you to control whether the importance sampling ratios are computed at the token or the sequence level. Okay, and then it basically just adds this toggle here, or this kind of conditional here, where either you have this to get the importance weights or this sequence. And that's basically, once you get into GSPO, you realize that it's actually not, there's not a lot to it. It's basically just if GRPO token level, if GSPO sequence level. Okay, so let's actually look at the paper to see exactly what that means. All right. Current state of the art, our L algorithms exhibit severe stability issues when training gigantic language models, often resulting in catastrophic and irreversible model collapse. Okay, and this is something that we've seen in reinforcement learning since forever ago, but I would say the other kind of big time we saw this was when RLHF became popular, right? Where a lot of people started noticing that whenever you use reinforcement learning to push gradients into a pre-trained language model, you start to kind of drastically collapse the token distributions that come out, right? So what's one way to kind of, that still seems a little bit nebulous, like what the hell am I actually talking about? So what I'm actually talking about here is that this is a great visualization of a transformer, but ultimately what a transformer language model does, right, is it creates this, right? You have this token vocabulary, which is all the possible words that it can output. And for each of these words, there is a probability associated with it, right? So, for example, the sentence here is data visualization empowers users to visualize, and then this is now going through the model, and then at the end, you're getting, here's all the possible next words, right? And there's a probability there, right? So whenever people talk about this idea of model collapse, what that actually looks like in practice is that the richness of this basically goes to shit, right? Where suddenly, like, the one word becomes the only word, right? So, for example, the next word visualize here will be like 99%, and then everything else is 0, right? So you want this to have like a richness to it, a nuance to it, right? So there's a lot of different possible paths that the model can go down, right? Whenever it goes into these different, because each of these kind of starts like a sentence, right? So like once you get into this token, then there's a next token that's probably more likely too, right? And the richness of those different possible paths that the model can go down is a feature, right? But once you start pushing gradients with reinforcement learning into these models, they start closing out some of those branches, right? So it's almost like RL is really good at telling the model what not to do rather than necessarily kind of encouraging, like it literally encourages better behavior, but the easiest way to get a higher reward is usually to stop doing the things that give you bad rewards. So what that ends up looking like is that they just kind of narrow these language models into very kind of narrow paths, right? Okay. Damn, all right, you guys are, maybe I'm going to have to stop answering every single question because there's a lot of people asking questions right now. Do you think reinforcement learning has a long way to go, or do you think reinforcement learning is just a small trick to make LLMs better? I think it's way more than just a small trick, right? I think the only examples we've seen of superhuman intelligence like AlphaGo are based on reinforcement learning. So I largely think that now when we're already seeing people talking about moving from AGI to ASI, right? I think RL is going to play a huge part in that because it's really the only way to go out into the universe of possible tokens and find the reasoning traces that are actually high value and then train on those. It's like the only way to get superhuman training data no matter what your domain is. Is GRPO only useful for LLMs? No, you can use it for pretty much any environment. We'll see here. That's what this paper here is, flow matching policy gradients. This is basically RL for things like robots, speech, audio, kind of anything like that, right? This is not really GRPO, but you can use it on GRPO. They just don't do it in this paper. If there is some paper about reinforcement learning docs does not bring new knowledge, reinforcement learning is the only way to bring new knowledge, right? That's the whole Move 37 and AlphaGo, is that what you're doing in reinforcement learning is you're actually exploring the space of tokens, right? So whenever you're doing supervised learning on, let's say, the internet, which is basically what pre-training is, right? Is like, it's supervised in the sense that you're taking this sequence and then you're automatically creating this data point where, hey, the beginning of the sequence should be what you take in, and then the output, the next token, right? So it's self-supervised because you're not necessarily providing that label as a human, but it's basically just a giant supervised learning task, right? Where you can create the input and the output, and you can create basically unlimited amounts of inputs and corresponding outputs. But when you're doing that in a pre-training situation, you're only exploring the sequence of tokens that are basically available on the internet, right? So there's no new exploration of possible sequences of tokens. Versus in reinforcement learning, you're actually generating the data that you train on, right? So you're actually finding new sequences of tokens that have maybe never been said before, right? So why did AlphaGo achieve superhuman Go playing performance? It's because it played a bunch of games and in that way discovered, right? It discovered new games that had never been played before, and there was winning moves in those games that never had been played before that humans had never even discovered. So when you're talking about discovering new knowledge, reinforcement learning is really the only way to do that. Okay. Let's get back to this paper. So I have some stuff highlighted, which I thought was the most important, but we'll go through all the highlighted stuff in the papers, and then we'll go into the, we can just kind of more freely explore here. So all of these papers all start with PPO, right? They're all, again, reinforcement learning papers that kind of are doing a variant of GRPO, and in order to do a variant of GRPO, you usually have to explain GRPO, and in order to explain GRPO, usually you have to explain PPO. So pretty much all these papers start by explaining PPO. I think this one had the best explanation of PPO. So this one had the laziest here. So I think this one here. This is a slightly different paper, but some of these papers just don't care, and they just give you PPO in like one sentence, one paragraph. But some of these actually take a little bit longer to explain. Okay. Policy gradients. We study on-policy reinforcement learning, which is when you have policy gradient techniques which bypass the need for differentiable environment rewards by weighting action log probabilities with observed rewards or advantages. Okay, so usually when you're doing any kind of gradient descent, and most machine learning is doing that, right? You need this notion of differentiable, right? You're ultimately doing this back propagation, which means you ultimately need the chain rule, which means that ultimately every node or every part of your computational graph needs to be differentiable so that you can basically take the gradient of it, right? This is why, for example, Gaussian splats were huge, right? Because someone discovered a rendering pipeline that was fully differentiable, which means you could push gradients into it, and that's how we got Gaussian splats. So in reinforcement learning, right, your environment is not differentiable, right? So like the dynamics of like a robot moving in the real world, you can't calculate a gradient through that, right? So what you're going to be doing instead in this reinforcement learning or policy gradient kind of paradigm is you're going to create a gradient, right? Which is basically just a slight adjustment of your weights in the neural net in order to move your policy around in that kind of weight space. And then that policy will produce actions where the actions that have high likelihood have a better chance of giving you high reward, right? So it's basically giving you actions that are better. I think there's a sentence here that kind of explains it. increase the likelihood of actions that result in higher rewards. That's like ultimately all you're doing in reinforcement learning, right? So the likelihood of actions, and in pretty much all of these, because reinforcement learning kind of comes from the kind of more basic fields of statistics and information theory, it has inherited that terminology. So a lot of this terminology here basically comes from this, right? So this is kind of the core tenet of probability here. This is Bayes' rule. This is where these terms come from, right? So for example, the likelihood is the probability distribution of the observed evidence given a parameter value. Well, what's the evidence? The evidence is this, the probability distribution of the observed evidence independently from any parameter value, right? So this is the evidence, and this is the probability of the evidence given X, which is your actual parameter. The posterior is basically the flipped of that, the probability distribution of the parameter X given the evidence. And then the prior, this is Px, the probability distribution of the parameter independently from any evidence, right? So this is where all the terminology that they use in here. So whenever they're using things like likelihood, prior, posterior, it's all just statistics. That's what they're kind of referencing here. So increased likelihood of actions that result in higher reward. What's the kind of more natural way of understanding that? The likelihood of actions, another way to just really think about what this is just these probabilities here, right? So whenever I'm looking here, right, the word create has a low probability, or 20% lower than visualize, which has whatever, 50%, right? So whenever they're talking about increasing the likelihood, think about this instead as a Go playing AI, right? And then each of these possible tokens here is like a possible move or a possible action that the Go AI could do. So increasing the likelihood of actions that result in high rewards is just another way of saying we want to adjust these probabilities right here such that the actions that give me high rewards, or basically the moves that are good and make me win the game, those moves have a higher probability than the moves that are shit and make me lose the game, right? So what you're doing when you're doing reinforcement learning is you're just ever so slightly changing the weights for that, right? So we're going to stop by here for a second. All right, so this is something that I've shown before. This is a visualization of a loss landscape, right? So what I'm trying to show you here is the process of kind of gradient descent. So every single point on this surface is basically a model, right? So you have the model here, and then you have the model here, you have the model here, you have the model here. These are all the same model architecture, but different values for the weights, right? And whenever the model is here, given some input, it's going to produce some output, and that output is going to have some loss, and then that loss, you can plot it, right? So you can see that here, this model has very high loss. This model also has very high loss. The model here has very low loss. So what you're doing when you're doing gradient descent is you're basically guiding the model into some point in this weight space, right? The space of all possible values for all the weights in the neural net. And usually it's not two-dimensional like this. It's usually way higher dimensions, right? But gradient descent is basically rolling down this hill. I think the marble rolling on the hill is probably the best intuition or analogy that you can possibly have in machine learning. But that's all you're really doing, right? So every single time you're pushing a gradient in a reinforcement learning context, you're basically just taking a little step, right? Which is kind of why where this clipping comes from, right? So vanilla policy gradient is valid only locally around the current policy parameters. Large updates can lead to policy collapse or unstable learning. So PPO incorporates a trust region by clipping the likelihood ratio, and that's where the P in PPO comes from, right? So PPO stands for proximal policy optimization. The PO, policy optimization, just basically means that you're optimizing the policy, right? You're taking steps in the policy is the neural net. So when you're optimizing the policy, you're changing the weights in the neural net. So you're basically moving around in this space. The optimization means that you're hopefully moving towards some minima, right? And the proximal refers to the fact that you don't want to move too much, right? So one of the problems is that, and this is kind of where this whole idea of on-policy RL versus off-policy RL comes in, right? So you see that a couple times in these papers, this idea of on-policy versus off-policy. So on-policy means that the data that you generated that allows you to push the gradients was generated by a policy or a model that is basically the model that you're pushing the gradients into, right? So let's say you generate a batch of training data here. As soon as you take a policy update or you push gradients into the policy is no longer going to be here. Right now it's going to be here. So if you now use the data that came from this policy to try to push a gradient on this policy, it's not even the same policy anymore. So there's a little bit of a drift kind of that happens there, right? So in PPO, the original kind of formulation, they introduced this idea of clipping, right? Where you basically clip that gradient update, which is a kind of a way to intuit that, is that here, this is a visualization that uses the learning rate, but it's basically the same kind of concept where if you have a very high learning rate, every single step moves you very large, makes a very large movement in this landscape, right? So every single step results in a drastically different policy than the one you had before, right? And we know from before that if you take big steps in policy space, you're going to end up the data that you collected before is going to be less and less applicable. You have this kind of drift effect. It starts to kind of smell like off-policy reinforcement learning, which is not anywhere near as efficient and stable as on-policy reinforcement learning, right? So by clipping, you're effectively taking smaller little steps, right? You're only ever taking little tiny steps. And by taking little tiny steps, you're closer to this kind of on-policy RL kind of paradigm where the data that you're training on, that you're using to push gradients with, is kind of created from the same model that you're pushing gradients into. Okay. Is maximizing probability with respect to the label different from maximizing it with respect to the reward? Kinda, yes. The reward comes out of the environment, right? So there's the environment, you kind of treat it like a black box in reinforcement learning, right? It's like something happens in the environment and you get a reward out based on your current state and your action, right? So you could kind of just say, hey, so for example, the core idea of imitation learning is that I have some trajectories of human collected or human controlling a robot. And rather than saying, okay, this action goes to the environment and gives me this reward, and I'm going to create some gradient based on that reward, in imitation learning, you're more saying, okay, in this state, the human had this action, so therefore I'm just going to create a gradient that just mimics that action, right? So imitation learning, you're basically just copying the action, or I guess maximizing the label that the human created for this given input. But there's a hidden assumption there that the human is acting optimally, which is almost always not the case, right? What you really want to formulate your problem is in such a way that the gradient is kind of coming from the reward. And that's what this, for example, advantage is. So that's actually a great way to kind of introduce this idea of the advantage here. A hat T is an advantage estimated from the rollout's rewards RT. The rollout is basically just, you can think of it like one episode, or like doing inference a bunch of times in the environment and creating a sequence of state, observation, action, reward. State, observation, action, reward, right? So that kind of continuous, or not continuous, but like that sequence of like, I was in this state, then I took this action and I got this reward. Now I got this observation, I fed that in, got this state. So that kind of chain or sequence is the rollout. Rollout is just kind of different terminology for it. Think chain of thought would be another kind of an LLM term for this concept. Okay. Flow policy. Let's go back to here. Once they start talking about flow, we're going to go back to this one over here. Okay, so the advantage A hat T of Y of T is estimated by another value model. The core challenge of PPO in practice lies in its heavy reliance on the value model. Specifically, the value model usually has a similar size to the policy model, introducing considerable memory and computational burden. So one of the problems with the PPO is that in order to get this advantage, you need a value model, right? And that's basically now you have two models. Now you have the actual model that is the policy, and now you have the model that is the value model. And anytime you have two models like that, right? So the GANs, the generative adversarial networks, are kind of a similar situation where you have this generator and then you have this discriminator. And because of that, training them is a huge headache, because kind of if the discriminator and the generator ever kind of like one gets a little bit better than the other, then it becomes this huge pain to optimize. So PPO has kind of a similar situation, not in that it's a pain, because usually the value model, you don't have the same kind of generator discriminator dynamics that you have in the GAN, but the problem is that now you have a whole separate model that you have to basically perform inference on, right? And having two different models that you have to load onto your GPU can be quite annoying. And that's actually one of the problems in this FPO paper, is that because it's just built on PPO rather than GRPO, you can see that not only do they have the policy model parameterized by theta here, but they also have the value function model, which is parameterized by phi here. So you have two models, right? And the whole advantage of GRPO, this is how they're setting it up, right? So they start with PPO, then they talk about GRPO. So the whole innovation of GRPO was that we get rid of this value model. We bypass the need for the value model by computing relative advantage of each response within a group of responses. Okay. So rather than the advantage coming from this value model, we're instead going to calculate the advantage by just taking the mean of the rewards of some sampled batch, right? So we have some experience, some rollouts, then we know what the reward for those is, right? Which is coming from the environment. Or if you're doing math, right, think of it like the actual heuristic validator that's telling you, is this answer correct to this math problem? You can basically take the average for a bunch of those. Here you see this mean, standard deviation, and use that as the advantage. So now you don't have to have this value model, which means you saved a bunch of inference, you saved a bunch of training headache having different machines, one that has the policy, one that has the value model, right? Like you got rid of some complexity, you simplified the training process, and you get more efficiency and throughput, right? Anytime you can kind of simplify some of these things, usually it means that computation, right, or that computational graph can be more efficiently implemented in parallel in a bunch of GPU nodes, which means that you can get more throughput. And because pretty much every machine learning algorithm scales with compute, right? If you can simplify the compute graph or improve the way that compute graph maps onto an actual computational mesh, then you can basically just churn through that faster and more in parallel, and that gives you a smarter model at the end of it. Flow match policy gradients with GRPO next, 100%. They kind of set it up in this paper. They don't. So this is like I think like with these type of ideas, right, this is at the very beginning. So at the very beginning of the idea, right, you don't have the kind of bandwidth. You're still kind of developing the idea. It's still very early. So all the examples that they have here are things like Grid World, the Mujoko Suite. If you've never seen the Mujoko Suite, is there examples of this here? Mujoko Suite. Most of you probably already know this, but this type of stuff, right? So it's like these little toy environments where you learn to stand up with a humanoid, or you try to move this little half cheetah forward, right? So I would say FPO, or this flow matching policy gradient, is still very, very early, right? So it's still just these toy environments, but there's nothing that prevents you from putting this on top of GRPO or GSPO, right? So yeah, you can 100% take this paper, do it on top of GRPO or GSPO now, and that's a new paper. So yes, that's a totally valid research direction that people are probably working on right now. In fact, I bet you one of these authors is 100% working on putting this on top of GRPO. Okay. Is there any other things here that I missed? Reweights the model's existing behaviors to sample correct solutions more efficiently. Does reinforcement learning really incentivize reasoning capacity in LLMs beyond the base? I don't know if like incentivizing reasoning, I guess you're like correct there. It's just kind of a weird way of thinking about it, right? So the reinforcement learning is basically just a search process is kind of the way to think about it. It's generating a bunch of data and then searching through that data for the data that has high reward, and then using that to push gradients into a model so that it can then search through more data and then find the data that has high reward and then push those gradients into the model. So it's like reinforcement learning is really this kind of like search process if you think about the whole thing, right? You're just searching through the space of all possible actions, or in language model, all possible token sequences, in order to find the token sequences that have a high likelihood of producing a high reward, right? So in reasoning chains, it basically means like, here's this long sequence of text, which is, we think of it as like a reasoning chain, but really what it is just like this giant sequence of text that leads to the right answer. And RL just allows you to kind of search the space of all sequences of text to find those that give you to the right answer. Would be great to do flow matching with reasoning traces. Yeah. It kind of like, I think diffusion is actually kind of starting to look better and better and better, right? Like diffusion language models, definitely a secretly hot space right now. That's just based on last week's stream where we were looking at autoregressive versus diffusion in this paper that was basically showing to us that in these kind of diffusion models, you have this natural data augmentation, which is coming from the fact that you're kind of starting from noise, right? So in this FPO, right, I'm kind of cutting to the chase here, but like, how do they get samples for this? Well, it's just Monte Carlo, right? So it's basically Monte Carlo draws of time step and noise. So what is this noise? That's basically data augmentation. So flow matching and diffusion in general, because you have this noise, right? It's a natural form of data augmentation, which means that in low data regimes like robotics, right, these diffusion setups are going to train better than the kind of autoregressive setups. Okay. And they even say it here, right? Sample count NMC is a useful hyperparameter for controlling learning efficiency, which is just a fancy way of saying that, hey, when we're using a Monte Carlo type approach and a kind of training pipeline that has this kind of built-in data augmentation because of this noise, then if you just literally crank up the compute, which is just cranking up the number of samples you do with this Monte Carlo, you're going to get better results, right? Which is the bitter lesson. So this is good. This is like following the bitter lesson. If you have some kind of Monte Carlo thing, you can just crank up the number of samples and you're going to get a better model. In this case, a better grid world exploration, right? And grid world is just kind of like 2D, like start here, get to the goal. So it's like kind of the simplest possible kind of little environment. Okay. Let's come back to the GSPO paper. So GRPO is basically PPO, but get rid of the value model and replace it with this kind of average approximation or group approximation of the advantage. So what is GSPO? Okay. So GSPO, I'm going to kind of cut to the chase here. The core principle of GSPO is that we replace token level importance weight with sequence level importance weight. So an importance weight, and this idea of weighting in general, is that whenever you're pushing gradients into a neural net, right, you kind of have to decide what the size of that step is, right? So what is the learning rate really deciding? The learning rate, which I'm changing down here, and you can see that it's basically adjusting the step size here. What the learning rate changes is basically how much are you actually changing each little weight in your neural net, right? So like, let's say one of the values for your weights was 0.5. Are you changing it to 0.51 or are you changing it to 0.7, right? So the magnitude of that change, you can kind of trace it through this entire gradient calculation, loss, all of that, and there's a bunch of different little things that affect that, right? So learning rate is one thing that changes the magnitude of that. Importance and these weights are basically another little thing that changes the magnitude of that, right? So importance weighting is this idea of like, I'm going to change the relative weight that each of the different things inside, for example, my sequence, or maybe the weight of each little data point in my batch, right? But ultimately what I'm doing is I'm basically changing the magnitude of how much I'm changing my weights, right? So that's this whole idea of weighting is like, okay, well, how are we weighting each of the data points that I'm putting into this batch of data that I'm then using to calculate the gradient for my model? So in GRPO, each token had an importance weight. So if you actually kind of zoom in here, right? So token level importance weight means that the weight of this specific token, right? How much this specific token is going to change the parameters of my neural net is based on the probability here, right? So this yi comma t given x yi less than t. So this is basically all previous tokens. What is the next token? So this specific token, the probability of this specific token given all previous tokens, and over the probability of this specific token given all previous tokens for the old model. So see this pi old, or theta old theta? This is the whole kind of on policy, off policy kind of situation where theta old is going to be this, and then theta is going to be this. So once you change your policy, right, you push a gradient, you now have two different models. You have the model from last step, and you have the current model. Right? So that's what this theta old and theta is. This is the current model, and this is the old model, right? So in the current model, the probability of this specific next token, this thing here, right, is going to be slightly different than the probability of the old model, right? In the old model, maybe the probability for this token create was 20%. And then in this new model, the probability for that token is maybe now 15%, right? So, I mean, this is it's a little bit more nuanced than that, right? Because we're talking about likelihoods, and this is log likelihoods, but that's just kind of unnecessary nuance, right? In your head, just think of this as like a probability. So this is like the 20% chance probability, and now this is a 15% chance probability. So if that specific token suddenly became 5% more likely with your new model, that tells you something, right? That tells you that, okay, there's something about this token that has changed after we pushed a gradient into this, and that's what this little ratio here is telling you, right? So what GSPO, which is the new variant of GRPO, is it basically just says, okay, rather than doing it for this little token, so at a token level, let's do it at a sequence level. Okay, so basically rather than doing it for each individual one, we're doing it for the entire sequence. So, okay, cool, like, what does that really mean, right? So in this paper, they have this whole kind of like theoretical kind of justification for it, right? So some papers, they kind of have an idea, and then they use experiments to kind of validate that idea, right? So they just kind of like, hey, I randomly thought of this idea, and then here's the experimental validation to show that my idea works, right? Other ideas and other papers kind of come from the other side, where they're like, hey, here's a theoretical understanding as to why this idea works, and then I'm going to give to you the experiment. So it's kind of like that. It's bottom up from the theory rather than kind of like the more kind of empirical scientific way of like, hey, here's a bunch of weird results, and then let me find the thing that works, right? So it's like you can do science in both ways. You can kind of bottom up from the theory, or you can do experiment down. And this is even the case for physics as well, right? So like, there's theoretical physicists who kind of work in the theory space and then use that to get something that you can then hopefully prove in the real world. And then you have kind of more experimental physicists that are doing the experiments, and then eventually, hopefully, that leads them down to some kind of theoretical result. So here, the core principle in the theory that allows them to kind of justify this swapping out the token level with the sequence level is the unit of optimization objective should match the unit of reward. Since reward is granted to the entire sequence, applying off-policy correction at the token level appears problematic. This motivates us to forgo the token level objective and explore utilizing importance weights and performing optimization directly at the sequence level. Okay, so this is especially relevant for like math questions, right? So you have these math questions, and then at the very end, you get some reward. Okay, this math question, you got the right reward, or you got the right answer, which means we're going to give you a reward of 1, right? And then that reward is going to then back propagate through every single token, right? And in classic reinforcement learning, you have this like discount factor, and you're kind of basically just doing 0.99 times 0.99 times 0.99, and then you're using that to basically say, okay, well, token 100 steps before the final answer has this much reward. But that's kind of not correct, right? It kind of doesn't even feel correct. And the reason it doesn't feel correct is because really you only know the reward of the entire sequence, right? You know that this entire reasoning chain led to the right solution, but that means that you should really optimize for that entire chain, right? That entire sequence. You shouldn't be doing this token level importance weighting if the reward signal and from the environment is really coming at a sequence level. So that's the core intuition here for GSPO, is that like, hey, maybe this token level importance weight, we should just get rid of it and do this sequence level importance weight. And that's basically what these PRs are, right? So this PR, for example, in the TRL, the transformer, what does the TRL stand for here? Fuck, I already forgot. My brain is limited. Transformers reinforcement learning, something like that. Transformer reinforcement learning. I don't know if this is a good name for it. Because transformer is such an overloaded term. It could mean the Hugging Face Transformers library. It can mean the transformer architecture. Like, I don't know. All right, whatever. But if you look at this PR, right, like ultimately, the only difference between GRPO and GSPO is basically swapping this token to sequence level importance weighting, and that's literally what you're doing here, right? So you can see here you're summing over the whole sequence, and then here's that clipping. Okay. GSPO applies clipping to the entire response instead of individual tokens to exclude the overly off-policy samples from gradient estimation. Okay, so you can see here that same clipping, right? And anytime you hear that word clipping, just think of this little visualization in your head and think about that step, just kind of making it smaller, right? So like the gradient, you calculate it and it's saying, hey, take this huge ass step here. But you know that huge ass step is just going to lead you to some place that you don't want to be. So you clip it. So it's just a little tiny step. It's in the right direction, right? The batch is telling you the right direction to move in. But by clipping it, you're just ensuring that you're not moving too far away from your current policy so that your policy doesn't just end up in some other completely new space and it's completely off policy, right? You want to do this kind of like on policy-ish by clipping it, keeping close to the current policy. I think they have some good intuition here on policy, off policy that I think is worth reading here. So a large rollout batch size maximizes hardware utilization during RL. So what does this mean? So rollout batch size basically means a rollout is inference, right? So in order to produce a rollout, or in your head, think of like one of these chain of thoughts, right? You're performing inference, right? So you're doing this autoregressive generate a token, then put that in, generate next token, generate next token, generate next token. So that inference, that autoregressive inference, you're paying for that, right? You're paying for that hardware. So you want to maximize the utilization of your hardware so that you're getting more computation for the amount of money that you're putting into this, right? So increasing the batch size basically means that you're performing this rollout or this inference in parallel, right? So you're basically doing big batches of inference in order to maximally create a bunch of rollouts or a bunch of trajectories, right? So in reinforcement learning terminology, you would say by doing batched rollouts or batched inference, I am increasing the amount of experience I can collect and thus increasing the amount of data I can use to then push gradients into my model. But the problem when you're doing this large rollout batch size is that you end up creating a bunch of data. Okay, so it's standard practice to partition a large batch of rollout data into multiple mini batches for gradient updates. Okay, so whenever you're doing inference to collect a bunch of experience, right, or think about it in the Go world, you're creating a bunch of new games, a new bunch of synthetic games that you've created, you're not going to be able to push gradients from all of that data that you just created, right? So you're going to have to kind of chunk it into little pieces, right? And each of those little pieces or these little mini batches, they're going to inevitably introduce an off-policy learning setting, right? Where what's going to happen is that you're using a policy to collect this giant data set here, right? This large rollout batch. As soon as you push that first mini batch, now you're currently in a different place, right? So you collect a bunch of data and your model's right here. You take one batch update. Now your model's here, right? So now if you're doing another mini batch, you're actually technically off policy now, because now the policy that was used to collect that data is here, but you're now here. You take another mini batch, now you're here, right? So as you kind of push each mini batch, you're kind of going more and more off policy, right? The responses Y are sampled from an old policy rather than the current policy being optimized. So this explains the necessity of the clipping mechanism, which prevents overly off policy samples from being involved in gradient estimation. And I think this is an important thing to realize, is because a lot of a lot of people talk about on policy and off policy like it's some kind of like black and white, like this thing is on policy and this thing is off policy, but it's way more of a continuum than that, right? It's like on policy basically means that the experience or the data that you're using to push gradients into your model is like coming from that specific model. Off policy just means that it's not the same model, and there's kind of a degree of off policiness. Okay. All right, people are dogging here. Maybe changing the weights of the model, but training a LoRa and then changing the influence of each LoRa would be nicer. Yeah, I mean, there is all kinds of fancy 500 IQ LoRa stuff that we've looked at. You know, people using LoRas to kind of like they heavily quantize models, and then they can use a LoRa to kind of reduce some of the degradation that you get from the quantization. LoRas are obviously very popular. Maybe not as much anymore, but like whenever Stable Diffusion was there and image generation was done with these open source models, people created these LoRas that allowed you to create different versions of Stable Diffusion. So I think, if anything, I would say LoRas are probably becoming less and less prevalent, you know, but there's probably still a bunch of alpha out in the LoRa world where you could use them in interesting ways with reinforcement learning. GSPO on TTS would be awesome. Lots of text-to-speech models have got good results on GRPO using a word error rate. Yeah, there's still a lot. This is why reinforcement learning is kind of super interesting right now, is because we've basically drastically advanced, right? We're no longer just talking about PPO on Atari or PPO on, or like some variant of that crap on like the DM control suite. It's like we're now starting to use new RL algorithms on these new problems of like language models, right? So it's kind of like we're in a new world here of reinforcement learning, and there's just so much different things that you can explore. So there's actually, I would say, if you're in some kind of academic situation where you're trying to find out, you're trying to find some niche where you can kind of discover a new algorithm or some kind of new interesting thing, I would say reinforcement learning is a very interesting place to be playing right now. That's a shame. I always thought LoRas were cool. Yeah, I mean, they are cool, and I'm not saying they're dead, right? Like, pretty much like all of machine learning, things go out of favor and then they come back into favor. So I'm just saying that right now, LoRas are like, I don't see them as much anymore, right? Still very relevant. Very easy to swap them around at runtime with a VLLM. Yeah, that's another paper that we read, right? Where basically, it was this paper that we read where it was like about having a ton of LoRas in an inference situation where basically you have one kind of base model and then you can hot swap LoRas. So you can have like one model with 1,000 LoRas, and then you kind of swap in those LoRas at inference, and you can get a bunch of different behavior out of that one model because it has all these different LoRas, right? But the problem with that is that it introduces a bunch of complexity, right? Now you have to have a bunch of LoRas that you're storing on this device, and you have to be able to hot swap them in depending on the inference request. It's actually a lot easier to just have one model that can do all of those things, right? And that's kind of what mixture of experts is, you know? So for example, one thing that they talk about a lot in this paper is that in mixture of experts models, which they're all mixture of experts now, right? So like I think even the OpenAI open source model, it's all mixture of experts. So what is mixture of experts? Let's take a second here to look at that. Mixture of experts is this. So if you look at this, these two things basically look exactly the same, right? You have your inputs, those are the same. You have positional embeddings, those are the same. You have your layer norm, here's your self-attention, that's all the same, that's all the same. But what's different here? Well, this part is different here, right? So a core part of the transformer is basically this feed-forward network, or the fully connected, or the multi-layered perceptron, if you really want to think of it that way, even though most people don't call this the MLP, but it's basically your actual fully connected neural net, right? And in a mixture of experts model, what you're doing is you actually have many of these feed-forward networks. And then you have this little thing here called a router, which uses the input to determine which router to route to, or which expert to route to. So it's basically choosing which of these feed-forward networks is the most relevant for the tokens that I am consuming right now in order to produce the next token, right? And really what this is it's kind of a cheat code, right? The problem, what mixture of experts solves is that ultimately, when you're performing inference, you have to fit this entire thing into your GPU VRAM, right? Your GPU memory, right? So that means that if a bigger model is smarter, you always want to have a bigger model. And what do you eventually run into? Well, at some point, your big model isn't going to fit into your GPU VRAM. Okay, so how do we make an even bigger model that somehow bypasses this GPU memory constraint? Well, we can do this mixture of experts. So we can have a huge model. This model has basically more parameters, right? Has more of these feed-forward networks, and some of these aren't even on that GPU, right? So like really what a mixture of experts model is a cheat code to have a bigger model by just having it not all on the GPU at the same time, right? So it's like whenever people talk about these mixture of experts models and they're like, okay, this many active parameters, what they're talking about is that only a subset of the parameters are being used for that specific next token prediction, right? So that means that all the other parameters don't need to be quote unquote active, which means they don't actually need to be loaded onto your GPU. And it's a little bit more complicated than that, because usually when you're talking about mixture of experts and serving that, you're talking about maybe having some kind of model parallelism, right? So your model is actually distributed over multiple GPUs. So maybe all of your weights are actually loaded, but only a subset of those weights are being used for the specific inference request. But mixture of experts is just a fancy way of increasing the size of the model so that it has more kind of capacity, right? Because a lot of people say that this feed-forward network here, this is where the actual kind of intelligence or like knowledge is, right? So like the knowledge isn't necessarily in the positional embeddings, right? The positional embeddings are just this kind of like function that says, where am I on this in the sequence? But really the knowledge, right? The factual knowledge, and probably also the kind of like intuitive knowledge is like here in this feed-forward network. This is where the actual intelligence is. So if we can increase the number of parameters there, then we can get a more intelligent model. But what happens with these mixture of experts models is that they're very susceptible to this model collapse that you get when you're pushing gradients with RL, right? So what is that? What is another way of thinking about that? Well, okay, if I'm pushing gradients with this RL, right, I might change the probability of this token, and it might be 6%, and now suddenly it becomes 0%, right? I create this reasoning chain. This reasoning chain leads to the wrong answer. So then whenever I'm pushing a gradient based on that reasoning chain, I'm basically saying, don't ever go down this reasoning chain, which means I'm zeroing out the probability of ever going down that reasoning chain, which means that whenever I end up doing this mixture of experts model, maybe it never ever routes to this expert anymore, right? So what mode collapse or model collapse looks like in these mixture of expert models is that suddenly you go from utilizing all of your experts pretty well and pretty evenly to suddenly like a bunch of your experts are never routed to anymore, and you just have a bunch of dead parts of the model, right? So you're kind of literally making the model smaller because this reinforcement learning gradient pushing is kind of catastrophically kind of shutting off parts of the model that just maybe don't produce the right things for that specific thing, right? So mixture of expert models are particularly susceptible to the model collapse of reinforcement learning post-training, basically. All right. Let's go here. Gspo. What is this? What am I looking at? So this is the training reward and training compute. So this is the model starts off and it's very dumb, and then it's getting smarter and smarter and smarter over time. And you can see GRPO, this is the blue line. So that's the token level importance. And this is the sequence level importance, GSPO. So in pretty much all of these plots, right, the red line is above the blue line, which means that it's getting more reward for less compute. So that's the evidence right there, is that, okay, it seems like GSPO, at least in these specific tests with this specific model, seems to work better. You know, now the Achilles heel of this is that, of course, this is only applicable to this, right? This is kind of my whole gripe that I had in the previous stream with people calling things laws, right? Like the scaling law and the test time compute law. Like, these aren't laws. These are just empirical observations that you can then turn into a hypothesis, and then you can use that hypothesis to extrapolate, but that's a completely different thing from a kind of a universal law. So, like any paper, right, they're going to try to convince you that this always applies, but it could be the case that if you had a different situation, you might find a model where GRPO and a model in an environment combination where GRPO works better than GSPO. But at least for the ones that they present here, GSPO works better than GRPO. And one interesting little observation, so a curious observation here, the fraction of clipped tokens between GSPO and GRPO, despite clipping significantly more tokens and consequently using fewer for training, GSPO still achieves higher training efficiency than GRPO. So GRPO's token level gradient estimates are inherently noisy and inefficient for sample exploitation. Okay, so what this is telling you is that they're looking at how many of the tokens are clipped. Right? So if you remember, clipping is basically whenever you take a step here, clipping is like reducing the magnitude of that step, right? That's kind of effectively what's going on. And when they looked at the amount of clipping that's going on in GSPO versus GRPO, you actually get more clipping in GSPO. So this sequence level importance weighting is somehow leading to more clipping. So wait a second, if you're clipping more, shouldn't that mean that your shit is, you're moving around more? So it means that you're kind of not optimizing as well? Well, actually, that's not the case, right? If I'm clipping more and I'm still getting better results, that means that the direction that I'm moving in is actually good, right? Versus GRPO, I'm not clipping, I'm barely clipping, and I'm still performing worse. So that means that each little individual step is probably more noisy, and that's what they're talking about here with this, the GRPO token level gradient estimates are inherently noisy and inefficient. So it's basically, this is just shit talking GRPO and saying that GRPO is kind of like this, where it's like moving back, it's like moving in all these weird directions, but it's not actually moving in the right direction, which is towards this pink circle, right? So GSPO, even though it's clipping more, it seems to be moving more towards the right direction. Okay. Let's see, there's one more thing I had highlighted here. When adopting the GRPO algorithm, the expert activation volatility of MOE models can prevent RL training from converging properly, right? So expert activation volatility, that's what I was talking about here, right? Where which expert are you actually using, right? So if this expert is activated, but this expert never gets activated, that means that you're doing something wrong, right? You ideally want to have somewhat even amount of expert activation. You want to be using all your experts. You want to make sure that every little feed-forward network is really being utilized to its full capacity, right? You're storing a good amount of intelligence and knowledge in each of those little experts, right? After one or more gradient updates, the experts activate for the same response can change significantly. Roughly 10% of the experts activated under the new policy are different from those under the old policy. That sounds pretty bad, right? Okay. GRPO with routing replay, GRPO without routing replay. So if we're in this MOE world, the routing and seeing which of the experts are activated is actually a very good way of determining whether your post-trading, in this case with RL, is actually hurting the model or helping the model, right? So you can actually go in. This is almost like a mechanistic interpretability, if you want to think of it that way, where you can always go and look at a mixture of experts model and see how it's routing the tokens and use that to determine whether the mixture of expert model is like cooked and it's basically just collapsed and it's only ever using one expert, or whether it's still a nice, healthy mixture of experts model that's kind of adequately using all of the experts. Okay. How's it going? Aries770 and Dan. The question is, if RL on text is the same as RL the AlphaZero style, can't you learn new formulas and equations and ways to reason? Yeah, you can 100% do that. The models are doing that, right? If you look at the reasoning traces for the model that solved, for example, the IMO gold, I bet you some of those token sequences are unique in that no human has ever produced that token sequence, right? That token sequence that led to some specific part of the proof for the IMO gold was basically a new scientific discovery. People don't think of it that way, but basically the reinforcement learning went out and it found this specific sequence of tokens that somehow ended up getting a higher reward on math problems, and now that is being used to solve new math problems. So in a way, that's new information discovery, right? So like this is happening all the time, except it's less obvious to us because we see so many different chains of or sequences of text that it's very hard for us to notice which ones are original sequences of text and which ones are basically just regurgitated from some other previous human. Okay. We're going to move into this paper here, but there was in order to do that, I wanted to show this paper real quick because I think this one kind of makes this better. So ARPO, but we're going to look at this one. Beyond the 80-20 rule, high entropy minority tokens drive effective reinforcement learning for LLM reasoning. So RLVR, this is like new terminology that's come into the world here. This is basically just RL with verifiable rewards, which is basically just rewards that you can verify, like code and math or something like that, right? And these guys were looking at the token entropy patterns in chain of thought reasoning. We observed that only a small fraction of the tokens exhibit high entropy and that these tokens act as critical forks that steer the model towards diverse reasoning pathways. Huh. Okay, so what are they saying here? RLVR largely adjusts the entropy of high entropy tokens. So what they're saying is that if you actually look at a reasoning chain, which is this sequence of tokens, the majority of the entropy is actually in one specific fork, right? So what that means is, if we go back to our visualization here, is that most of these tokens have a very low entropy. And a low entropy is something that is kind of, if you had a, so for example here, what would low entropy look like? Low entropy would basically be everything is zero except for one token, right? So that's low entropy because it's not random, because the next token is extremely obvious, right? There's like one token. It can only be this token, right? Low entropy. You can pretty much guarantee the result, right? High entropy would basically mean that a bunch of these tokens have equal probability, right? So you don't actually know which one, it could be any of these tokens, right? So that's what they're showing you here, is that actually in these reasoning chains, there's actually this kind of pattern where there's specific tokens that can branch off into a bunch of different paths, and these are the high entropy minority tokens. And then there's a lot of tokens that are basically just super low entropy, is just you're following this path, right? It's like once you start here, then you kind of already know what the next three sentences are, and you're just kind of going into the next sentence, you're just kind of regurgitating the tokens. So this is very important, right? Because it basically means that most of really what you want to be adjusting and modifying are these little fork paths, right? And in this paper, they did that, right? So they restricted policy gradient updates to forking tokens and utilizing only 20% of the tokens while maintaining performance comparable to full gradient updates. So training exclusively on the 80% lowest entropy tokens leads to a marked decline in performance. So this is rhyming a lot with what we were discovering in this paper here with the token level importance and sequence level importance weight, right? Where token level importance weight makes more sense when every single token is kind of like about the same entropy, so every token matters, right? But if we're kind of already starting to realize that, hey, the sequence matters, right? Or as how this paper's saying, this paper here is basically saying, hey, actually the entire sequence is really one chunk of a thing, right? It's like one big path, right? Because once you get that first token, all of the other ones are basically just low entropy, just, hey, I'm just kind of blasting out the rest of this path, right? So if you're trying to be efficient about the compute that you're using to train, then maybe you should focus your RL on these fork tokens, right? And that's what they do in this paper. So I thought this was interesting. This is the figure 2 in this paper, and they show you which are the tokens with the lowest average entropy and which are the tokens with the highest average entropy. So if you look at some of these, for example, frequent tokens with the highest average entropy, however, maybe, assume, right? So like after the word thus, there's actually this huge explosion of possible paths, right? So if you're like, blah, 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 thus, and then there's basically like 5 or 6 different, or probably even more than that, but there's a huge amount of different possible paths, right? So maybe reinforcement learning is less about thinking about each individual token and more about being like, okay, these are the high entropy tokens, and all we're doing is we're just adjusting the probability of each of those paths as soon as we get to these forks. And if we modify that, we can save a bunch of compute and still end up at the same post-trained RL model that is better at math and code. Okay. These are the least or the lowest average entropy right here. So for example, sine, cosine, ation, amplify. I think these are kind of interesting because it basically means that like as soon as you use the word theta, the next token is pretty much like you know exactly what that next token is. There's like a 100% chance of the next token being this and 0% chance for all the other tokens. So I thought this was kind of cool how this is basically just a bunch of weird like math symbols. And then this here is like these kind of like, I don't know what the English term for this is, but it's like the right after a sentence. It's like you basically say actually, comma, and then you have a whole sentence, but that whole sentence can be very different. You can have like 5 different sentences after the word actually. Chain of thought tokens with the highest entropy typically serve to bridge the logical connection between 2 consecutive parts of reasoning, while tokens with the lowest entropy tend to complete the current part of a sequence sentence or finish the constructing a word. Other tokens combine these 2 functions to varying degrees. High entropy tokens often act as logical connectors within and across sentences, such that wait, however, and unless indicating contrasts or shifts, thus and also showing progression or addition, or since and because expressing causality. Similarly, tokens like suppose, assume, given, and define frequently appear in mathematical derivations to introduce assumptions, known conditions, or definitions. So there's a bunch of other crap in this paper, but I thought that was really the most important kind of thing in this paper is that really that intuition that, hey, actually in these reasoning chains, it's actually a bunch of low entropy stuff, and there's really just these specific high entropy fork tokens, and that's really where you want to focus your RL. So that gets us to the next paper, ARPO. Let me take a sip of water here. Basically, we could split the sequence of tokens and use high entropy tokens as splitters and then generate variations. Yeah, and that's basically what this is. Okay, so that's actually a very good transition into this paper. This is ARPO, Agentic Reinforced Policy Optimization. This is kind of a cheese, you know, like this is one of those papers where like they use the word agentic just because they want to put that in there, right? Agents are hot, so it's basically just, the concept isn't that complicated, but by using the word agentic, they're trying to SEO a little bit more, right? So an increase in the entropy distribution of generated tokens immediately following interactions with external tools. Okay. So in these, when you're thinking about an agent, right? You're interacting with an agent such as O3, right? It has these tools that it can use. And those tools that it can use are kind of like this here, right? They're kind of like these paths, right? So what these guys noticed is that much like these guys noticed that, hey, there's specific tokens in these reasoning chains that are these forks, these guys noticed that, hey, right after or right before using these tools, or basically right after using these tools, you have a similar kind of situation where there's actually these high entropy, these kind of entropy spikes whenever you're kind of around this tool use, right? So for example here, tool call step 1, entropy, let's kind of zoom in here, it's kind of hard to see. Entropy visualization of Gaia, which I guess is like some kind of model. So you can see here, tool call step 1, you see this entropy? So it spikes up right after that tool use. So you're like, the model just called the calculator tool or the search tool or whatever, and you can see there's all this high entropy tokens right here. So this is where all the forks are being decided. It's kind of being chosen where you're going to end up. And then as soon as you kind of make a couple tokens, then the rest of the tokens are low entropy. So it's kind of like there's this relationship whenever you're training these tool calling agents in a reinforcement learning situation that you kind of want to focus in and around these tool calls, right? The initial tokens generated by the LLM after receiving each round of tool call feedback consistently exhibit a high entropy. This indicates that external tool calls significantly introduces uncertainty into the LLM's reasoning process, uncovering latent behaviors that remain underexplored. So, and this is really the point of this paper, right? So, okay, cool. You identified that after tool calls, you have a high entropy. So like, what the fuck does that do for me? Well, what that does is that basically if you're going to be training a bunch of reinforcement learning, you want to make sure that you're collecting data that is actually going to adjust your model in such a way that the probabilities of the tokens that are good are better, are like more prevalent, right? So the model, the policy produces actions that have a higher likelihood of producing high reward, right? So if you know where the entropy spikes are, because you know when the tool calls are, right? Anytime you call the tool, you like in the code, that's actually going into a separate code path and calling that tool. So you know where the tool calls are, which means that you know where all the high entropy stuff is, which means that you know where all that juicy data is, which means that with this ARPO technique, you can basically increase the efficiency of your reinforcement learning training pipeline. And here's the final sentence here, achieves this with only half the tool call budget required by trajectory level RL method. So if you're just like kind of naively just training on the whole individual token, kind of trajectory level RL as they call here, you can be much more efficient because you know that around the tool calls is where all the magic happens. So you're kind of focusing all your training around these tool calls rather than like the low entropy slop here, right? Okay, this is actually the same plot as this other paper. So if you remember this plot here, high entropy, low entropy plot, this is like the same exact plot. Frequent tokens with the highest average entropy. Start, now, information, determine, right? So it's like, that's the beginning. Frequent tokens with the lowest average entropy. Search, think, Python. Why is Python low? Because it's probably... Think about every time it uses the word Python, it's probably, let me write a Python script for that. And then it has to write a bunch of boilerplate. So it's like, as soon as it says the word Python, it's like all the tokens that follow that are basically low entropy. Like it's seen this a million times. It's just kind of going through the motions. So here's their kind of like fancy crap here. Branching high entropy tool use step. ARPO encourages broader exploration of tool use behaviors. So if you already know you're going to be forking a bunch, right, at this high entropy choice, then you can basically fork whenever you do this tool call. So do a lot of this kind of like sampling or basically branching out in and around these tools. When PFT exceeds a predefined threshold, it initiates a branch, branching Z partial reasoning paths from the current node, right? So PFT here is basically these hyperparameters here, and then this delta H of T, and this delta H of T is basically the entropy. So high delta H of T, high entropy, means that this PFT is going to be high, and that PFT, once it's above some threshold, then you branch. So this isn't like ideal. So for example, these are all hyperparameters. So this is a hyperparameter. That's some random number that some human chose. This beta is a hyperparameter. It's some random number that some human chose. This alpha is a hyperparameter. It's some other random number that a human chose. So like, this is a little sketchy. You know, you have like 3 different completely arbitrary numbers being used to determine with this branching, but what you gonna do about it? You know, sometimes you just gotta have some random arbitrary hyperparameters in there. Okay. I think that's, did I have anything else highlighted here? I think that was pretty much it. That's really the important concept. Is there anything else in here? No. Okay. So I think we can finally move on to this one. Sparse high entropy fork bodes well for distilling COT with flow matching. Maybe we'll finally be free of the yapping tax. Yeah, I mean, one way to think about this is that this isn't good from a computational standpoint, right? Where think about every single, you're putting the same amount of compute in between each of these nodes, right? The autoregressive transformer is using the same amount of compute for this as it is for this. But that's not really what you want to be doing, right? Like in practice, like in theory, I guess, or intuitively, you should probably spend more compute on this point here than you do between these two. So there's something fundamentally wrong with how we're treating these reasoning traces where if there's this outcome that a bunch of it is low entropy slop, and then there's these very important high entropy points, right? So really, we should try to fix that, right? We should try to fix the model architecture or some kind of, we should introduce something or find some solution to where we're spending more compute on these important decision boundaries here rather than spending all this compute just yapping, right? Which is kind of what you're saying, where it's like right now, these chain of thought kind of reasoning models, how much of that reasoning is just a bunch of low entropy slop or yapping, right? Where it kind of already knows what it was going to say and it's just going to spend the next 10 turns basically saying the 10 tokens that it already kind of knew. So maybe we should kind of shortcut that, right? So like maybe we could introduce special tokens that basically count as multiple, like make a token that is basically like a whole sentence. So now it can basically output that entire low entropy slop in one token and then move to the fork, right? Or another kind of interesting solution to this is this idea of like reasoning and latent spaces, right? Where your chain of thought is not like forced to be in tokens. It's basically doing it in some like latent space. So hopefully that latent space will kind of massage itself in such a way that you're not kind of just spending equal amounts of compute for this low entropy stuff. But I don't know, it starts to get pretty complicated pretty fast. All right, let's talk about this one. This one was quite popular. Flow matching policy gradients. On policy, let's look a little bit about here diffusion models. So diffusion models have become the predominant approach for generating images, videos, audio, and more recently, robot actions. So again, diffusion models are not different from transformer models. In fact, most diffusion models are a transformer architecture, right? But diffusion models are particularly good at these kind of continuous domains, right? So in robot actions, it's not discrete. So for example, a language is discrete in that there's a limited vocabulary of possible tokens. So really what you're modifying is the probability of each individual token at each individual step, right? So it's basically you have all these possible tokens and there's a discrete one. It's going to be one of these, right? That's kind of what discreteness means, is that there's a limited set and you're going to have to pick one. And I can enumerate that set and I know exactly, I don't know which word it's going to be, but I know that it's one of these, whatever, 200K words, right? 200K tokens. But robot actions are not like that, right? Robot actions, it's like the value for this joint can be 1.01, it can be 1.0014, it can be 1.001456, right? So it's like there's a continuous space of possible robot actions, which is where these diffusion models, same thing with images and videos, right? It's a much more continuous space. It's still discrete, right? So if you want to be like a, well, actually kind of person, you can say that, hey, actually all of these are discrete because ultimately we're putting this on a computer and the computer is representing everything with bits, which means that even an image is not a continuous space because at some point, right, there's boundaries, right? There's the uint 8 that represents this specific pixel color, like only has 256 possible values. So everything is discrete, but some things we call them continuous because there's just like a much larger space of possible values than for something like a language model with a limited vocabulary. So if you want to be cool, you can actually tell people that actually technically everything is discrete. And if you want to get super meta, even our world is discrete, right? So not everybody believes that, but I think the Planck length and the speed of light basically means that time is discrete and space is also discrete. So everything is discrete because everything is running on a computer. Okay. Flow matching simplifies and generalizes the diffusion model framework. It learns a vector field that transports samples from a tractable prior distribution to the target data distribution. The conditional flow matching objective trains the model to denoise the data that has been perturbed with Gaussian noise. Okay, so this flow matching policy gradients paper, one of the best parts of it is this blog post. So they actually released this very nice blog post with a very nice little visualizations, right? So whenever you see this here, a learned velocity field that maps from a simple distribution, e.g. Gaussian noise, to the training distribution. So that's what you're seeing here. This is the simple distribution. This is the Gaussian prior, right? So here's your nice little Gaussian, and this is all one-dimensional. And then here's your time-varying vector field. So let's kind of crank this a little bit down so it's a little bit easier to see. But what means here is that you have the time. So at each of these points, right, we have a little vector, right? That little vector points you in a direction. So in this case, for example, the vector's pointing you towards this red part, right? So each little particle here is kind of, if it spawns here, it's going to point here, and it's going to move towards this kind of red region, right? So this is a one-dimensional thing, right? So this is a one-dimensional example, and the second dimension here is the time. But what am I trying to say here? Learn velocity field. So it's time-conditioned velocity field. So at every single time, it's a slightly different field, right? So the field here at time 0 is different than the field here at time 0.8. But if you take a point in this field and you start from noise and you just plug that in to your model, which is telling you this field, right? And you just, okay, well, this model is telling me that the field at this point is pointing in this direction. Okay, so I'm going to move a little bit in that direction. Okay, now I'm going to try the model again, and it's telling me that at this point in time, and this point, I should move a little bit in this direction, and then a little bit in this direction, a little bit in this direction. Ultimately, what this velocity field or flow is, it moves from this Gaussian prior into this complex data distribution here, which is ultimately what you want. Right? This complex data distribution here, this is basically the image space, right? The space of all possible images. Or in robot actions, it's the space of all possible robot actions, right? So it's this incredibly complicated distribution, right? The robot actions that produce high reward in a 28 joint humanoid, right? Like, what the fuck is that distribution? Nobody actually knows what that is. So you're trying to approximate that distribution, and this flow is going to lead you from noise to that distribution, which you can barely understand. Very cool animation. Apparently he did this with, he vibe coded this, so. And the way that you do this, right, the whole reason that flow matching and diffusion models are really popular is because you can go backwards, right? You can start from this. Well, what your data set is a bunch of examples of this, right? So you can take any point in your data set and then basically just progressively add noise to it. And now you just created a learning target. So given this noise, lead to this output, right? So it's basically like a way to generate infinite data for a continuous regime, because you can just always add noise to make it more and more noisy. And the way that the noise works is that as you keep adding more noise, everything eventually becomes Gaussian noise, right? So that's kind of like another kind of part of the magic here, is that like you take any data set, any data distribution, such as robot actions or images, right? If you progressively add noise, it eventually looks like this prior, this Gaussian prior. So basically you now have I just love the idea of like an infinite data generator, because you can always add more noise. And this is kind of what we were talking about last week with the data augmentation that's built in explicitly into this. Okay. So this is conditional flow matching, and the conditional there means that you're conditioning the model that generates this flow or this vector field on something, right? So if you're generating images, you're conditioning on the prompt, right? So you're removing the noise such that you end up at a cat image, and that cat token is being used to condition this, right? So this flow is conditioned on not just the something like the text, but it's also being conditioned on the time. So it's like time conditioned. Why is there a space here? Supervised learning. What? Okay, let's go back to here. The learned velocity field is a continuous mapping that transports samples from a simple tractable distribution, e.g. Gaussian noise, to the training data distribution through ODE integration. This is differential equations. That's just basically saying that, like, hey, once you create this model that basically can create, or this vector field that leads you from the prior to the data, then you can just do standard differential equation, like, hey, just go here and then 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 go here, and then boom, now you're suddenly at your image of a cat, We already talked about this. This is their PPO explanation. Okay. And now this is where FPO comes in. So FPO is basically PPO. There are two key differences in practice from Gaussian PPO. So the first thing is that instead of updating exact likelihoods, we propose a proxy R hat FPO for the log likelihood ratio. Okay, so this ratio here, right, which is the difference in the likelihood between the old model and the new model, right? So the old model is here, and then this is the new model. So you took a little gradient update, now you have a different model, right? So there's some ratio there of like, hey, the old model gave me a 20% chance, the new model gives me a 15% chance. So that's what this little ratio is, right? But you might not necessarily have that, right? The probability of this specific action from this model and the probability of that specific action from the other model. So you're replacing that, right, with this R hat FPO, which is basically this flow matching. L hat, the loss for the conditional flow matching with the old model, and this is the new model, and then here's the action at time t and the observation at time t, right? So it's basically just what is the difference in this field between my old model and my new model. So the old model, right, if I sampled it at this specific time and this specific place here, it's giving me a little vector, right? The new model, if I sample it at the same time and at the same place, it's going to give me a slightly different vector. So the difference between those two vectors is this. So you're kind of, it's kind of a similar concept, right? It's like this tells you kind of how much the model has changed by looking at the likelihood of those actions. Here, you're kind of saying how much has the model changed by looking at the field that this CFM is giving you. For a given action observation pair, LCFM is an estimate of the per sample conditional flow matching loss, which is basically just this here, right? Here's your squared, right? So it's basically just the squared error right here, v hat theta. You see how it's also conditioned on the time, so you're also using the time in order to get this. And then here's your action with the noise. So your model is basically predicting this noise. And this noise is sampled from a Gaussian. So Ti in 0 and 1, that's this right here, time step 0 to 1. And then this epsilon I out of n0i, that's basically this. That's this Gaussian right here. So this is a Gaussian centered on 0 with basic or expected identity covariance, this I. The ratio decomposes into the standard likelihood ratio and an inverse correction term involving the KL gap. Maximizing this ratio therefore increases the modeled likelihood while reducing the KL gap, both of which are beneficial for policy optimization. Okay, so they basically go and then take this little proxy that they did, and they show that if you kind of replace it with this elbow, which is kind of a different formulation of the KL divergence, if you want to think of it that way, you can rewrite it like this. Right, so now you've rewritten it as this original kind of ratio that we saw before, and this new thing over here, which is exponent of the KL divergence over the exponent of the KL divergence. They call this the inverse KL gap. And KL divergence is basically just the distance between two different distances. So how different is my old policy from my new policy? That's basically what the KL is telling you. And this is basically some ratio of that. And reducing the KL gap basically means that your theta old and your theta are more similar. So the more similar your theta old and your theta are, the more stable, right, you're going to be able to train or push gradients, right? So that's a good thing. Reducing the KL gap is a good thing. You want to take little tiny steps. You don't want to have massive KL. The firm encourages the policy to favor actions with a positive advantage. So this is now basically the ratio from before, right? This kind of standard part of the PPO, where if you're making this higher, what are you actually doing? Well, what you're doing is that, okay, well, if this A of t produces high reward, you want this number, right? You want the probability of that high reward A of t to be bigger than the probability of the high reward A of t before, right? So if this A of t has a 50% chance of being selected and gives you a reward of 1. And in the old model, it had a 20% chance of being selected. That's good, right? Because that's going to make this number bigger, and that's going to maximize this. So ultimately, this what PPO is doing is it's changing the model such that you maximize the expected return, right? And if your actions that produce high return are getting more likely, that means that you're getting more return on average. So this little term that they formulated here is basically, it seems like if you decompose it into the likelihood and this inverse KL gap, both parts of that make sense, right? You're both increasing the likelihood of high reward actions and reducing the KL gap. So both are beneficial for policy optimization. Okay. I think we already talked about this, but basically they just Monte Carlo, right? So they're just kind of like sampling a bunch of noise and time steps. So you start with some data set of robot trajectories, and then you basically just add a bunch of noise and then use RL to create this flow. And now you have this flow, which will allow you to start from noise and conditioned on something, maybe on the prompt, if you're generating images, you should be able to get to an image of a cat. Or in a robotics use case, maybe your input is the current trajectory or something like that, and then the output is going to be the high reward action, right? So you're going from noise to the data that you actually want, which is like high reward actions in the robotics use case, or in images, it's like the actual image of a cat. Minimizing the conditional flow matching loss points the flow more towards A of T. Flowing A towards a specific action makes it more likely, increasing the probability of high advantage actions, making them more likely under the learn policy. And then Monte Carlo FPO can be trained to outperform Gaussian PPO even with NMC equals 1. That's important. It basically means that they're not just gaming this, because like one thing that they could have done in this paper is that because they now have this ability to basically create infinite training data, right? You can kind of say, hey, we're better than PPO because we have this built-in data augmentation, right? But by saying this, they're saying, hey, even if we keep the number of Monte Carlo samples low, which means we're not kind of cheating by just kind of increasing the amount of computation that we can use with this method, we still beat Gaussian PPO. So this sentence is important because it basically means that this paper is applicable. Basically, you should never use PPO. You should always use FPO. And then you should probably use FPO on top of GRPO. What am I doing here? This is the flow policy. Actually, I haven't looked at the chat in a second here. Let me see. Very cool animation. Yeah, these animations are great. I love this animation. This is going to blow up once the video modality starts becoming more common in the models. Yeah. If anyone needs some foundation, Rich Radke has a good machine learning course. Okay. Would it make sense to create different latent spaces, each capturing some frequency of details per image? So for example, like in latent diffusion model, right? So most people are aware of diffusion models for images, and when you're doing diffusion for images, you're not actually doing it in pixel space. So every time you see a diagram like this is actually wrong, right? It's not like you're adding noise to the cat image in RGB image. Like, it's not like you're literally adding noise to the cat image. What you're really doing is you're first encoding the image. So the image right here is going from image space or pixel space into this latent space, right? So all images are some vector, some point in this latent space here, which is created by this encoder decoder, right? The decoder will take you from that latent space back to the image space. But the diffusion, right, and the addition of noise and removal of noise is all happening in this latent space, right? And in this latent space, basically you just don't have any intuition, right? It's like what is adding noise and removing noise in like a 1,000-dimensional latent space mean? It basically, there's no way for you as a human to understand what the fuck that means. So that's why in every single one of these diffusion pictures, they're always kind of showing you adding the noise to the image, right? Because that's a very intuitive way to understand it. Or in this diagram, this is a one-dimensional example, right? It's a one-dimensional Gaussian, and your target distribution is also the same thing, right? It's just one-dimensional. So everything we see is all just these kind of like simplifications, just for building intuition, but it's not actually what's going on. Do you expect mass production of humanoid robots before 2037? Yes. If you would have said 2027, I would say like 50-50. In some ways, we're already mass producing robots, right? We are like, if you look at the Unitree factory that makes the humanoids, they already have pretty good practices on. It's not like every single one of those humanoids is being created by hand by some Geppetto like dude who's like sitting there like polishing every little. No, it's like the Unitree quadrupeds are coming out of a production line that is optimized and that looks like a mass production line, right? But there's also a difference between cranking out 100 things and cranking out 1,000 things and cranking out 10,000 things. So humanoid robots are not at the point where people are cranking out 10,000 humanoids, right? We're still in the like 100 humanoids, 1,000 humanoids. But 2037 is very far in the future. I feel by 2037, for sure, there's going to be factories that crank out thousands of humanoids per day. Could you explain the MOE and how it's different from the LLM? Yeah. I did explain it already, so I apologize for those that heard it, but mixture of experts basically is the same thing as a normal LLM, except you're taking one specific part of the LLM, which is the feed-forward network, and you're replacing it with a bunch of different feed-forward networks. So each of these little squares is actually the same number of parameters as this big square here. And by having a lot of these little squares that you then have to route, you can then have more parameters, which means your model has more capacity, which means your model can store more information, which means your model is smarter, right? So a mixture of experts is just a way of getting around the bottleneck of GPU memory, right? Because what's limiting you in terms of the size of the model that you can use is basically how big is your GPU memory, right? So in a mixture of experts model, you actually have a larger chunk of the model is actually not necessarily being used. So it's really just a big model of which you're only using one smaller part of it, right? So mixture of experts is just like a big model. It's just that only part of it is being used, and you're using the this router kind of determines which part of it is being used. Unless they are soldiers, soft robotics is the way to go. Yeah, kind of like inflatable robots you're talking about, Dan. There are things like that. There's inflatable robots. There's robots that you can basically just like, there's the little like slug that drags itself. Soft robotics. Yeah. These things. These are kind of like a gimmick though. Like really, I don't think any of the, like every single one of these soft robots is basically like a demo, you know, like these aren't being used in production. These are just like in some kind of specific lab and they just turn it on to do a demo for the people who pay for the lab, you know? I think what I highlighted here is the computationally intensive parts, right? So if you remember, right, the problem with the PPO and the reason that GRPO succeeded is because it simplifies PPO by getting rid of this value model. But if you look at this FPO paper, they still have this value model, which means that not only do they have to have the GPU memory hold this policy parameters theta, this policy model, it also has to hold this value model. And you now not only are pushing gradients into the policy model, but you're also updating the value model. So it's like you have like twice as much crap, right? You don't just have one model that you push gradients into with the group advantage like you do in GRPO. If you're kind of using classic PPO, you have two different models. Now you have two models and you have two gradient updates. That's why you want working alongside you, not some Tesla bot who will hit you and injure you for life. Yeah, but why are you still working around the Tesla bot? You know, I think this ends up looking like the lights out factories, you know, where you have a factory where what's the point of having the lights on? Robots don't need the lights, you know? So therefore we turn the lights off. So it's a similar thing. It's like, oh, well, you need soft robots so that they don't hurt the humans that are working with them. Well, at some point there's no humans working with them. The robots are working by themselves, you know? So as soon as you have enough autonomy in robotics that you can get rid of the human part, it simplifies the entire equation, right? So yeah, like I worked for Amazon Robotics. That was like the first job I had out of college, and I worked for Amazon Robotics, and I was working in these giant warehouses, basically doing this like heuristic path planning with thousands of robots in parallel. And there was a huge amount of complexity in the interface between the robots and the humans, right? So there was like this whole, like, you have to put fences and you have to have e-stops and you have to have all this kind of complexity, like safe. So like anytime the robots move, there's like this complicated kind of wrapper of like try accepts, basically, where it's like everything has to be like safety checked before you can do any kind of motion. And all of that was kind of annoying, right? Like you can see how eventually if you don't have any humans in the factory, then you don't need any of this crap, right? You don't need to have these e-stops everywhere. You don't need to have all this special safety crap, that all this computation that you're wasting just doing all this like double checking, triple checking that there's no humans in the path, right? You can just get rid of all of that, right? Because there's no humans there. Do you think gradient descent will stay, or do you think something will replace that? I think gradient descent is always going to be there. Even a neural network that outputs weights for new neural networks, you're going to use gradient descent to optimize that neural network. Gradient descent is like an extremely, it's almost like at the bitter lesson level of kind of like sacred, you know? The bitter lesson is actually a law. I would say that's more of a law. And I would say gradient descent is also kind of more towards the law scale of, or the law side of things, where it's just like, it's a universally the best way to optimize things. So I would say gradient descent stays, bitter lesson stays. I think they even mention here, more samples can improve learning without requiring more expensive environment steps. So what are they talking about here? What they're talking about here is that environment steps is how you collect data for example here, right? Whenever you're doing GRPO, the signal is coming from the environment, right? So you have to basically, each of these XYIs here, of which you're taking the mean and the standard deviation, these are experience. You had to pay for that experience with rollouts, right? So you had to actually put this model, put this policy into a server and run inference on it to collect a bunch of rollouts or a bunch of experience to do that, right? So that's expensive environment steps. But this FPO, you don't have to do that as much. And the reason you don't have to do that is because the way that you're getting your data is from basically taking your existing stuff and then just adding noise to it, right? So you can take your existing data set and get much more juice out of it because you can just keep infinitely adding noise and creating basically these input-output pairs of like, here's the thing with noise, and then here's the thing without noise, and then here's the same thing with slightly different noise, and then here's the same thing without the noise, and then here's the same thing with slightly even different noise, and then here's the same thing without noise. So it's like you can kind of like infinitely generate data like that in a way that doesn't require you to have expensive environment steps. Now, you still need to have an environment and then take steps in it, but maybe not as much because you have this kind of natural data augmentation. Here's a little interesting result. FPO performance is close to that of Gaussian PPO when conditioning on all joints and surpasses it when goals are reduced to the root or root plus hands. So they have a little thing that shows that. Yeah, so this is like the humanoid, right? And the humanoid has joints, and each of those joints is some continuous number, right? And then you can say your joint space is basically all these joints. So think about like some vector that has maybe like 20 something numbers in it, and each of those numbers represents one of the joints, right? So this is now just the position of the hands and the position of the root or the waist. So what they're saying here is that one way to show that FPO is better than Gaussian PPO is that when you condition on all joints, so if Gaussian PPO and FPO are given the entire humanoid, right, all the information, then they both kind of end up at the same place, right? But if you give them only the root and hands, right, so they only get access to the information of the hand position and the root or the little waist, then we see this huge difference between FPO and Gaussian PPO, which basically shows you that whatever magic there is in FPO is leading to a much stronger robustness to sparse conditioning. And when you're doing robotics, you're almost always sparse conditioning, right? Because it's like, think about all the information that you're not giving it. There's like a million, think about if you had a robot and you had like 100 cameras looking at it, right? And then you reduce that just to one camera looking at it. Well, you would say, okay, well, the one camera looking at it is sparse and the 100 cameras looking at it is dense. So people don't even realize that everything you're doing in robotics is already sparse to begin with, because the amount of input data that you're giving to your model is already just like such a narrow, thin slice of all the information you would need to actually understand and produce intelligent behavior. Right, so you're just getting like one grainy little picture of the gripper and like maybe the position of the joints, but it's like there's so much more information that you could be using to produce a better output. So in a domain like robotics where you have very sparse kind of input, FPO seems to perform better than PPO. What is MetaClip 2? CLIP is a contrastive language image pre-training. It's basically a model that allows you to take text and images and embed them into the same latent space so that you can compare, right? Apparently clipping is a hip hop group. MetaClip 2. Apparently the MetaClip 2 is also like a VR clip. Here we go. See if they have a good picture of clip. Okay, I don't actually know what MetaClip 2 is, but I know what clip is, right? And there's a lot of different clips. You know, there's OpenAI has a clip. Meta has clips. So MetaClip 2, I guess, is the second clip. So some other clip that they just recently released. Train on English, train on non-English. Okay, so this is interesting. So again, I haven't like read this paper at all, so I'm just kind of saying random shit based on like the 5 seconds that I've looked at this. But like whenever you're training clip, let's actually look at the original clip neural net. Right, so whenever you're training clip, you have an image and then there's a corresponding caption. And what you're basically doing is creating this text encoder and this image encoder that basically project into the same space. So this vector that represents that text, it's going to be close in space to the vector that represents this image, right? So now, why would you do that? Like, why is that useful? The reason it's useful is because now you can take any image and any text and say, does that vector have a high cosine similarity to the image? If that's the case, then that text is probably relevant semantically to that image. If the text has those two vectors are pointing in completely opposite directions, that means that text is probably not related to the image at all. So this clip model is very, very useful when you're training other things, perhaps stable diffusion, a bunch of other different things, right? Like these two paired encoders, which can transform an image into a vector and a text into a vector, and those vectors can be related to each other, is a very useful thing. So it seems here that Meta probably took clip and realized that, hey, if we train it on not just English captions, but we train it on like Chinese captions, then it gets better or something like that. Train on worldwide. So that's my 5-second take on MetaClip 2, having not read the paper. Multimodal clip. Loic Caban, isn't genetic evolutionary algo search even more bitter lesson pilled? Yes. Evolution scales and search scales. So I would say the bitter lesson basically just says that any approach which performs better with scale is going to work better over time, right? So diffusion, because you can always add noise and kind of create infinite data by just taking your current data and adding noise, right? You can just keep increasing this Monte Carlo number here, this NMC, because you can just make that bigger and bigger, this NMC, and it gets better and better results. That's bitter lesson, right? That's basically saying that this is a good algorithm because we can just keep cranking up this NMC, keep cranking the amount of compute we put into this, and it's going to get better. Evolution is the same way, right? Evolution is kind of like a search process. You have this generation, mutation, then you filter, selection, right? But that entire loop, the more times you run that loop and the more mutations you make and the more selection you do, the better the ultimate result is. So evolution is also something that if you increase that computational scale, it gets better, right? Search is the same way. The more you search, right? So here, if we go back to our thing, the bigger you make this rollout batch size, right? The more experience you collect allows you to get better, allows you to better sample, find those move 37s, and then put those via gradient descent into your model, right? So like search is something that also increases with computation. So yeah, bitter lesson is an intuition that basically says if your technique can scale with more computation, your technique is going to beat out the other techniques, even if the other techniques are fancier. Can you give us 3 to 4 line explanation of GSPO? Here it is. This is the PR for GSPO in TRL. Right here. And this is the 1, 2, 3, 4. Here's the 5-line explanation of TRPO or GSPO versus GRPO. GRPO is token level importance sampling. GSPO is sequence level importance sampling. Here's the same thing, but in math. Token level importance weight and sequence level importance weight. And then in plain English, GSPO is basically treating the entire sequence as more important than each individual token. And we saw from another paper that we looked at today that this actually seems to be very applicable to reasoning models, because in reasoning models, there's some tokens, these high entropy minority tokens, that are kind of deciding the entire sequence for you. So it's almost like this entire sequence here is really just one thing, right? So the optimization should be happening at the level of this entire sequence, because these other blue tokens here are basically just low entropy slop that comes out of this high entropy fork here, right? Which is the unit of optimization objective should match the unit of reward. So if the unit of reward is coming from, hey, this entire sequence leads to the right reward, then you should basically, your GRPO shouldn't be looking at each individual token. You should just do the whole sequence. So it's almost like the same way that GRPO was a simplification of PPO, GSPO is a simplification of GRPO. Do you think this monolithic training is the way forward, or the future would be more freeze a lot and just train one layer at a time, more like we learn a new concept by connection to the old ones? I think people already are doing that. So there's a lot of that going on. For example, in distillation, like people will kind of freeze different parts and then prune specific things. Like there's a lot of like kind of this type of surgery that you're talking about, where it's like you're doing one layer at a time. Like for example, vision language models are like that, right? Usually you have an encoder, which is pre-trained, and you have this little connector. You have a language model, you're freezing the encoder, you're training the connector, then you're freezing the connector, and you're pushing gradients. So it's like, there's already a lot of this kind of like layer surgery kind of going on, but I don't know if you want to look at that from the concept of, from the perspective of the bitter lesson, right? It's like, does layer surgery and like little tiny, does that scale with compute? No, it scales with engineers, right? The more engineers you have, the more clever you can be about like, okay, let's remove this layer and then we'll put a little LoRa and then we'll quantize it. Like, that doesn't scale, right? Versus monolithic training scales with compute. So I would say that eventually all that kind of like layer surgery goes away and we are training one layer at a time. I guess training one layer at a time is, I don't know. I don't have a good prediction on that. I can't see the future for that. Tech 300. I think research on reinforcement learning is increased day by day every week. Yeah. I mean, that's kind of what the point of this stream was, right? It's like there's this kind of Cambrian explosion of policy optimization. Look, policy optimization. Which is policy optimization? Is just neural net pushing gradients into a language model. Missed the live session. Who are you? That's 100. Pratik. That's a great little pun there. Well, the thing to do for regressive models could be add tokens and say delete the NPass tokens. Is Mamba stuff still around or dead? I haven't like heard much about it, but I mean, it has a bunch of good properties, you know, kind of like the infinite context length, the hidden state, you know, there's some good stuff there, but I don't know. Definitely less papers around Mambas right now, but maybe it's just because I'm not looking at them. You know, that's also part of it. It's like, I don't feel like I'm getting necessarily a good view of all the research that is happening, you know, because one, a lot of the research is now secret, but then also because the way that I get my information is from these kind of feeds, right? These kind of like social media feeds. So like when I click on a reinforcement learning paper, the algorithm gives me more reinforcement learning papers. So I'm sitting there and I keep clicking on reinforcement learning papers, and in my mind I'm like, wow, look at all this reinforcement learning stuff. It seems like it's getting super, super popular, but really what's happening is the algorithm is just being like, oh, this guy likes reinforcement learning. Let's just give him more reinforcement learning. And like, little do I know, there's all this stuff going on with Mambas in the background that I'm just not seeing because the algorithm doesn't think I like Mambas, right? So it's like, yeah, I don't know if I'm just in my own kind of echo chamber of like algorithmic feeds, or if it actually is the case that RL is really popular. What about Gaussian splats? Actually, if you guys want to talk about Gaussian splats, so this is a project that I work on called Tatbot. It's a robotic tattoo, but I recently made a little Gaussian splat for the latest version. So here's a Gaussian splat of the hardware V0.4 for my tattoo robot. So good. Look at that. The one thing I really like about Gaussian splats is that they're viewpoint dependent. So like you see this, the back of this computer is like slightly reflective. So if I change the viewpoint, you can see how it changes the appearance. I just think that's so cool. Right? So for example, something like this, that's not reflective. It looks the same from every single angle. But things like the screen that are reflective, you know, they change. You see how here it's a little bit more green, and then you move here, it's a little bit more black. The downside is that the lighting is baked in. Yeah, the lighting is baked in, so it's kind of like a frozen moment in time. You can see how like the lighting here is baked in. But compare that to, for example, this. This is the same data set, but meshed. So this is basically now you take those images and then you create a mesh from it. And you can just see how much, like some of it is nicer. You can kind of see the pattern a little bit better. But look at just how shit, like look at this. It didn't even get the screen. It just basically is just this big hole, right? Because it looks different. Because whenever you're creating this mesh and you're doing this kind of photogrammetry, right? You're finding correspondences between images, but there's no correspondence between the different viewpoints of the screen, because in one thing it has a high reflection and in the other thing it doesn't have that reflection. So because photogrammetry is very susceptible to view dependent effects, you get these like kind of like weird, like look at this, it does the what the fuck is this? It's like it can't see that, versus if you go to the splat, right? Look at that. It gets the cables perfect, which is, I think, super cool. Gaussian splats. I'm still a believer in Gaussian splats. All right. Probably I'm already over, but I should end this. Can Nerf do the same? Nerfs and splats are pretty similar. I know that's kind of like heretical for me to say, but they're basically like a learned representation. I think splats are a little bit better than Nerfs, because in Nerfs you're kind of putting all this information into this fucking arbitrary multi-layer perceptron, this kind of like this black box. You don't know what the fuck is going on. Versus like in a splat, it's like the representation is more explicit. It's like you're literally, here's the actual little dot, and you can look at that dot and you know where that little dot is in space, and you can say, I don't want that dot, right? You can crop, right? Like, for example, here in this Gaussian splat, I can crop this. I can say, okay, well, this little dot here, I don't want it. There you go. You can't fucking do that in a Nerf. The Nerf is like, it's just a neural net that's producing this output. But like, how do you crop something out of a Nerf, right? Like that you can't even do that. It's like implicit inside that neural net. So that's why I like splats a little bit better, is because like they're explicit, but the benefit is that the Nerf is tiny, right? So you could put a Nerf on like a tiny little Ray-Ban Meta glasses, right? So you can imagine, like, if let's say you're in the future and you're talking to someone via your AR glasses, right? Is the face that's talking back to you that represents that person, is that face a splat or is it a Nerf? If it's a Nerf, it's actually cheaper, right? The inference on a Nerf is actually easier, especially for something super small like AR glasses, right? So there's kind of a push and a pull there, where more explicit methods like Gaussian splats are better because you can edit them. It kind of works into the existing 3D workflows where you can crop and edit and do things like that. But Nerfs have this kind of just, the fact that it's all implicit makes it better from an inference, especially on an edge device. So I don't know which one is going to be successful. I feel like maybe one thing that people get wrong is they think that as we move into the future, like everything converges, but I think it might actually diverge, right? So it's like, think about something like music or art, right? Like as we move into the future, you get more genres of music. It's like the music is exploding into all these different possible genres. I think maybe technical solutions is going to be like that too, where it's like, rather than suddenly everybody starts writing the same code or everybody starts using Gaussian splats, everybody starts using the same stuff. It's like there might be a pattern where it actually gets more complicated, where there's like your glasses use Nerfs, but when you use your screen, it's using splats, and whenever you're using it over here, it's using some other third thing that we haven't even discovered yet, voxels, right? So like, it might be the case that we see like kind of a Cambrian explosion of different 3D representations rather than kind of a consolidation. Yeah, especially if AI writes the software, then basically if intelligence used to be a bottleneck because every single implementation has to be done by a human, then, you know, each implementation is quite expensive. But if AI is doing all the implementation, then it's very cheap, right? This kind of starts to become the idea that some people say, where it's like every UI is just rendered or created on the fly, right? So it's not like one engineer at Facebook creates the UI and then everybody uses that UI. It's like there's 1,000 different UIs that are each kind of generated kind of like ad hoc by some ML or some agent that generates that UI for this specific screen and generates the UI for this specific headset. So every single different screen and headset uses a different UI that's just kind of generated by an LLM, rather than having to have kind of a human that has to generate each of those. So there's like a limiting factor there. I'm way over, so I'm going to have to close out this stream, but let's do a little summary. So today's stream was called GSPO, FPO, ARPO. We basically reviewed 3 different papers in the reinforcement learning space, basically different variants of the PPO, GRPO algorithms. We have GSPO, and which is implemented in all the open source reinforcement learning libraries pretty quickly. The reason they were able to implement it quickly is because it's very similar to GRPO. We also looked at these two, ARPO and this kind of related paper, which basically shows you that maybe when we're doing reinforcement learning, we can be a little bit more intelligent about where we kind of sample experience from, right? And it seems like in these tool calling agents or in some of these reasoning agents, there's specific points in the sequence where you have high entropy, and then most of the other points are kind of low entropy. So kind of focus in your exploration and your branching on those high entropy points is probably something useful. And then we also looked at this paper here, FPO, flow match, which is basically taking the kind of flow matching from the diffusion world and applying it to RL, specifically on top of FPO. I would say this is probably the most preliminary work, so everything here was done in kind of toy environments, so there's definitely a lot of possible exploration and future research in this direction, but it seems very, very promising, especially for something like robotics. But yeah, that's basically it. You can find the notes here, so here's all the different links. And yeah, appreciate you guys hanging out. Thanks, Ed, Open Room, Spiral Bell, Dan, Aries, Pratik, NLP Prompter, Mark, Sid, Josh, Loic. Who else? I'm going to keep scrolling up here. Aries, Calduz, Dan, Julien, PW, Lil KM, Shortvid, NLP. If I missed your name, I apologize. But thanks everybody for hanging out, and have a great weekend.